Have you ever really stopped to wonder why your TV picture is just flawless, even when you're in a car or on a train, or how your digital radio just doesn't cut out? We completely take it for granted, but behind that perfect signal, there's this hidden super high-stakes battle going on, a battle against time itself. It's a fight waged in microseconds by engineers, all to keep our digital world perfectly, and I mean perfectly, in sync.
So in this explainer, we're going to pull back the curtain on why that perfect timing is absolutely everything for modern broadcasting. We'll look at the master clock in the sky that makes it all possible, and then explore what happens when that crucial signal just vanishes. From there, we'll follow the engineers who put these clocks through their paces and figured out what really makes them tick.
All right, let's dive right in. To really get what's going on, we first have to wrap our heads around the incredibly clever system that makes modern digital TV work in the first place.
Now really think about it for a second. How can you possibly get a perfect signal from a whole bunch of different transmitters, all broadcasting on the exact same frequency, without them all just crashing into each other and turning into a chaotic mess of interference? Well, the answer is, you have to make them work together like a single, perfectly coordinated orchestra.
This is what's known as a single frequency network, or an SFN. I want you to imagine a huge group of drummers spread out all over a city, and their job is to play the exact same beat at the exact same time. If they are perfectly synchronized, what you hear is one powerful, clean, crisp rhythm. That's an SFN. Every single transmitter has to send out the exact same data on the exact same frequency at precisely the same moment.
So here's the bottom line. If just one of those drummers, one of these transmitters, like the exciter you see here, is off by even a tiny fraction of a second, you don't get a clear rhythm. You get noise. You get a mess. And in the world of digital TV, that mess means interference, it means lost data, and for you, sitting on your couch, it means a frozen screen, or as one report puts it, a complete loss of service that can last several seconds.
Okay, so how in the world do you get every single transmitter in a countrywide network to stay in perfect time? Well, you give them all the same ridiculously accurate conductor. You give them a master clock that's literally in the sky.
And that conductor? It's the Global Positioning System. Yeah, GPS. We all think of it for getting directions, but its real superpower is time. That constellation of satellites gives us an ultra-precise universal time and frequency signal that's available pretty much anywhere on Earth. It's the ultimate metronome for our planet's technology.
So at every single transmitter site, there's this special piece of equipment called a GPS disciplined oscillator, or GPS-DO. The easiest way to think of it is as a very, very, very good stopwatch. It has its own internal clock, of course, but it's constantly listening to those GPS satellites to correct itself, making sure its timing is always spot on. Problem solved, right? Easy peasy.
Well, not quite. What happens when the conductor suddenly goes quiet? What happens when the GPS signal, for whatever reason, just disappears?
Now this is what's so cool about this slide. It's not a simulation. It's a real-world failure. On September 21, 2011, engineers at the Italian broadcaster Rai Group saw this pop up on their test gear. That line, which should be perfectly flat, suddenly just takes a nosedive. The clock has lost its reference point and it's starting to drift away from perfect time. For a broadcast network, this is what that report called a danger bell.
And this isn't just some abstract problem for a bunch of engineers in a lab. That drift you saw on the graph translates directly to this, a loss of service for you, the viewer. Your screen freezes up, the signal just drops out, the whole beautiful, elegant system just falls apart because one little component lost its sense of time.
This state has a name. It's called holdover. It's when that GPS-DO is basically flying blind. The GPS signal is gone. Maybe there's some interference, maybe the antenna's view of the sky is blocked, and now its internal clock is just left to run on its own. And just like a cheap wristwatch, it's inevitably going to start to drift.
This holdover problem was a really serious threat to the stability of their whole network. So the engineers at the Rai Group, they decided to launch a full-on investigation. They set out to figure out exactly how these supercritical clocks behave when they're put under pressure.
And this was no simple test, let me tell you. They built a custom analysis system to simultaneously measure the performance of 7 different GPS receivers against a master reference clock. They put all the antennas up on a roof with a perfect view of the sky and just started logging data, day in and day out.
Then came the real test. They deliberately blocked the GPS signal, forcing every single one of those clocks into holdover. And this image just illustrates their findings so perfectly. Look at all those different colored lines. Each one is a different clock. Some of them barely move. Others drift away nice and steady. And then you've got a few, like the red and orange ones, that just go completely haywire. They're losing time at a terrifying rate. But the real aha moment, the big discovery, came when they turned the GPS signal back on. Now, most of the clocks, they just snapped right back to the correct frequency. They were back on beat, sure, but all the time they had lost, it was gone. Gone forever. They were a few bars behind the rest of the orchestra. Except for two of them. Look at the brown and green lines on that graph. They don't just jump back. They start this slow, gradual climb, actively making up for the time they lost. This was the key.
So this right here is the crucial difference. A standard receiver, it fixes its frequency, it gets its speed right again, but an SFN-ready receiver does something much, much smarter. It doesn't just correct its frequency, it gradually makes up for the lost phase, that's the actual time that slipped away, and it brings its internal clock back into perfect, beautiful alignment with the rest of the network.
What this whole investigation showed was that, you know what, not all clocks are created equal, not by a long shot. And it led to a really clear set of rules for what makes a GPS receiver truly good enough for a critical single-frequency broadcast network. So here are the rules. 1. During holdover, the clock can't drift too much. That's a given. 2. When the signal comes back, it has to gradually recover the lost phase, not just snap back to the right frequency. 3. That recovery has to be slow, it has to be gentle, so it doesn't cause some sudden jump that knocks the whole transmitter offline. And finally, number 4, if the clock drifts so far that a safe recovery is just impossible, it needs to be smart enough to just shut itself down to avoid causing chaos across the entire network. So that perfect TV signal you get in your home, it's the end result of this hidden battle. It's a fantastic reminder that the technologies we rely on the most, the ones that seem the most flawless, are often built on these incredibly clever layers of engineering, all designed to handle failure with grace. And that leaves you with a final thought. What other invisible systems that we use every single day are fighting this exact same constant battle against microseconds? Think about it. The synchronized trades on the stock market, the stability of our power grid, even just the data packets flying across the internet. They all depend on a hidden, constant battle against the unstoppable drift of time.